it's my pleasure to introduce Pedro Ribeiro from the University of York, computer science. And he will talk to us about a Unary semigroup trace algebra. The floor is yours, Pedro.
Thanks, Peter. So, hello, everyone. I'm based at the University of York. I'm actually in a so-called RobustArt group, which is one of the largest groups in the world working on software engineering for robotics. And our approach consists in using heterogeneous semantics to capture several aspects of relevance for robotics, namely reactive behavior and time, via the unifying theories of programming, which is a relational framework suitable to giving semantics to different programming paradigms. And in this context, trace algebras are useful to abstractly characterize trace structures, and namely to facilitate the use of theorem proving using Isabelle UTP. So today I'm going to talk about the development of this Unary semigroup trace algebra, abbreviated as USTA, as a contribution towards mechanizing synchronous process calculi in the UTP, namely a family of time process calculi as well. So I'll provide some motivation for the work and describe how this relates to the UTP, and in particular its implementation in Isabelle UTP. I'll then show how the USTA is constructed and briefly discuss the instantiations of some concrete trace models. Then I'll finalize with some summary about the current and future work. So really the motivation here is that different trace structures capture different aspects, such as behavior. For example, you might have finite sequences where you have events A, B, and eventually C. So, if you worried about safety, for example, in the context of CSP, this is something that is adequate. The addition of refusals, that is, the events that are refused, allow you to reason about liveness. For example, here you have that after event A, the set with the only event E is being refused. And richer structures are possible, namely when taking into account aspects such as time. So here's a different sequence where you have pairs, and each pair records information about a different time slot. So in the first time slot, the event A has taken place, which is the first component of the pair, and the event E is being refused, which is the second component of the pair. And then during the second time slot, nothing happens, but A and E are being both refused. So what do they have in capturing? Well, they capture some kind of sequentiality. So you usually have some kind of prefix relation. So if this is just events, it's just stating that S is a prefix of T exactly when there is some Z, so that if S is concatenated with Z, then you obtain T. But if you have richer trace structures, then you might have questions regarding the relation between the refusals. So if you have subset closure, for example, that might be something you need to consider. And again, if you have time, are these things related? Yes, we want them to be related irrespective of the change in the refusal, in information being captured in the refusals. And that could be, for example, if there is some internal behavior that the process is doing and it suddenly changed the options that are available to its environment. So what do these things have in common? Typically, they're reflexive, transitive, and optionally antisymmetric, which means you might have an order or even a pre-order. So, as I said earlier, trace algebras are useful for the unification of semantics in UTP, and namely in its mechanization Isabelle UTP. So my colleague Simon Foster proposed a monotrace algebra. It's a structure with three components. You have a type T for the trace, you have a concatenation operator, and you have an empty trace, epsilon. These four axioms define a left cancellative monoid. And really the insight from my colleague was that for several of the theories we are interested in UTP, the prefix relation can be defined in a generic way. So provided that concatenation satisfies these four axioms, then the relation is an order. However, this is not entirely adequate if you want to capture theories where your trace structure as a prefix relation that is a pre-order. So how does this relate to the UTP? As I said, the UTP is a relational framework suitable for giving semantics to different programming paradigms. Here's a tree that sketches some of the theory dependencies in the UTP. So relations are at the very bottom, and then from relations we define the theory of designs that characterizes total correctness, and also a theory of reactive processes where we have these traces. And then combining these two, we get the theory of reactive designs, which allows us to give semantics to CSP and UTP, for example, and other theories. And in particular here, we're interested in giving semantics to synchronous process calculi. So the monoid trace algebra is used to define this reactive process theory. So, and the results are used by the theories above it. So here what we want to do is to generalize these reactive processes further. So what is the UTP theory? Well, UTP theory has three components. It has an alphabet. So we have alphabetized relations for recording the observations. So for example, here we have TR and TR prime of a type T, with TR for recording the before value and TR prime for recording the after observation. We then define healthiness conditions that define the valid predicates via fixed points. So here we have, for example, that R1 states that the trace can be monotonically increased, for example, extending your trace with further observations, with further events, or advancing time, for example. R2, on the other hand, is defined with substitution and states that the process must be insensitive to the trace, to the previous trace. So it says if we substitute TR for the empty trace epsilon and TR prime for the difference between TR prime and TR, then we should obtain the same thing back. R3 characterizes the intermediate observations, saying that if the process is waiting, then it behaves as the identity on the left-hand side there, or as P if the previous process has terminated. So that's captured via an additional variable in the alphabet called weight and weight prime. The combination of these healthiness conditions is the functional composition of R1, R2, R3. And from this, we can define the operators of the language. So here's a very small example of skip, which is the process that terminates immediately. Here it's being defined as a reactive design because we're applying R to a design that has a precondition true, so it can always be applied. And as postcondition, it states that the value of the trace doesn't change, and furthermore, it terminates, not weight prime. So the goal here is to widen the reactive theory foundation of UTP to accommodate synchronous process calculi. So what are the challenges here? Well, first of all, as I hinted earlier, the prefix relation is a preorder because we have that refusals may change during the current time slot. The second challenge is if we look at those healthiness conditions, we can see that the fixed epsilon is not quite suitable. And indeed, if we look at some of the existing work in the literature, we find that R2 is defined in a different way. It's actually a non-empty sequence with one pair whose first component is an empty sequence, but the second component is actually a value that depends on TR. It's a second component of the last of TR. So, and as I presented earlier, the original trace algebra is defined in terms of concatenation. So what are the problems for this? Let's look at the slots themselves, the pairs. So first of all, if you try to define concatenation for the slots, what we can do is we concatenate their history, so the first component of these pairs, but we need to do something about the refusals. So we throw one of them, we keep only the right-hand side one. And similarly, if we define subtraction of these pairs, we need to do something about the refusal. So from this, what we have, well, we have that concatenation based on this is not going to be injective unless we start having things like multiset refusals, for example. And that means the induced order from concatenation is a preorder, it's not an order. So we have a problem. And as I already said, the version of R2 is not quite adequate because, again, we have a fixed element epsilon and we need to account for further information. And here's the minor observation regarding mechanization, as always, that these slots sequences are non-empty. So they're not sequences that may be empty. So how can we accommodate these trace structures? Well, here's my solution. So let's pick the existing trace structure, right? We for sure need to change R2. So let's look at what we need to target. So we have this sequence with only one pair whose second component depends on the value of TR. Well, we can replace that with a function. So let's call it phi of TR. Okay, so instead of a fixed epsilon, we have this phi function. Now let's look at the axioms. Can we change and drop some of them? Well, we certainly want associativity so that we still have a semigroup structure. So we just rename them to user one to make it clear that we've gone through that particular axiom. TA2, the monoid zero laws, actually what we need to do here is to replace it with just one axiom where we say that if A is concatenated with phi of A, then it's the same thing as A instead of epsilon. We still want it to be left cancelative. When it comes to zero-sum laws, again, we do something similar. Again, we adopt phi, and we adopt phi of B. So we say that if A concatenated by B is equal to phi of B, then it must be the case that B is itself phi of B. Okay, so this is an analogous construction to the axioms that we had previously, but instead we have a function phi instead of a fixed element epsilon. And so that means we have this unary semigroup. And actually by construction, we have that phi is idempotent function. So now we have that the prefix relation is defined exactly as before, but we have a different set of axioms. And we have that provided that we have this structure, then the induced prefix relation is preordered as we require. Subtraction is defined analogously to the monoid trace algebra. I didn't show that earlier, but again, here it is. So we say that if A is a prefix of B, then if we subtract A from B, then it's the C. So here's Russell's definite operator, such that A concatenated with C gives us B. And otherwise, it used to be epsilon, but here again, what we do is say it's phi of A in all other cases. Okay, so now what have we constructed? Well, first of all, we have that if we fix phi to always be the value of epsilon, then we obtain exactly the same structure we had before. We still have a monoid trace algebra, which is nice. So we are at least as expressive, and that's a comforting result. Now, what changes? So let's look at some of the laws that the existing trace algebra satisfied. So we had a least element where epsilon was a prefix of everything. Now we have least elements because we have this function phi. So we have that phi of x is always a prefix of anything else. Similarly, we had in the previous case that subtracting epsilon from x yielded x. Now we have subtracting phi of y from x yields x. TS2 is a bit more problematic, even if we, so just to show it again. So if we subtract from x, some x from epsilon, we obtain the epsilon. If we now do the same thing with phi, well, this actually doesn't work. Now, this is not quite a problem because all the results that have been constructed so far, in particular, all those theories above reactive processes don't rely on this. So we're okay with that. TS3, again, we do something similar. We have phi of x instead, and TS7, we have something very similar again. So structurally, these are very similar. Okay. So now, is this structure that unique? So I struggled a while looking at the literature in semigroup theory to see what did this construct yield. So we actually have this unary semigroup whose function phi satisfies some of the axiom of restriction semigroups, but not all. So in the paper, I go into a bit more detail on this. But surprisingly, it satisfies a known class of semigroups, which is called a Wright-P-Hirschman semigroup, and that means satisfying the following axioms. So more details about this in the paper, but what's comforting about this is actually this is not as unique as I thought. So coming back to now that we've got the structure, coming back to the trace models. So what we want is to account for all such varieties of trace structures, right? And what we want to do as well is to have the ability to capture different prefix relations, so different orders, if you will, in an informal sense. So let me try and illustrate this instantiation for the particular structure. We have events, refusals, and time information. So what we need to do here is to, first of all, define what I call parametric pairs, P, which take two types, a type H for the history and a type R, which is unconstrained. And I'm going to assume that H is a justa. Okay, so it has its own concatenation and its own phi function as well. Then I'll define finite non-empty sequences, assuming that the elements are also satisfying the Euster axioms. And then I'll lift twice the Euster from parametric pairs all the way to the finite non-empty sequences. So as I said, we assume that the parametric pairs, the type H is a Euster. So we have a concatenation operator plus H here, and we have a phi H. So we define them as follows. We say that the concatenation of these two pairs is going to be the concatenation of the histories, and we take the refusal from the right-hand side pair. We define the unary function so that we apply, so the phi of P is the same thing as applying phi of H to the history component, leaving the refusal untouched. Then we can derive a subtraction as a lemma rather than as a definition, as I showed earlier. And that's nice, that's comforting. And more importantly, that means with this construction, provided that we have this Euster for the type H, then the parametric type itself is also Euster. So now moving to finite, so having defined that structure for pairs, I now move to the definition of the finite non-empty sequences. So here's a very simple definition for such a data type. We have a constructor for the case where we have just one element, and we have the cons as typical for these kind of structures. And we define concatenation assuming that this type sigma is a Euster. So it has its own concatenation operator, and it has its own phi function as well. So here's an illustration of some of the examples for this structure. As I have a singleton sequence, and if you have two non-empty such finite sequences, the way that they're concatenated is by concatenation of their elements using the concatenation operator from the sigma type. And similarly, if you have such a singleton concatenated with a larger sequence on the right-hand side, we concatenate A and B using the concatenation for sigma, and similarly for the other case. So now we have these sequences of timed slots, and we need to define a unary function as well. So our phi for these finite non-empty sequences. And we define it as follows. We say that phi of fs is the singleton finite sequence where the element is obtained by applying phi sigma to the last element of that sequence. So here's an example. So take the following trace where I have two pairs. So I have two time slots. Okay. So first of all, I apply, I use definition there. I apply a last to that. So I get just the last element, which is the pair where the first component I have event C and then A, B, and C being refused. I apply phi of P to that. So that means I apply phi of H to the first component, which is in this case, a sequence with the only element being C. And that is coming from, because for this particular example, I'm assuming that it's just a regular sequence of events. And so that becomes the empty sequence itself. So now that what does this mean in the context of R2 that I showed previously? Well, this means that if we define R2 where TR is being substituted for 5fs of TR, then the P must be insensitive to the previous history of events and time itself. So just as I've shown here, I've dropped all the time slots before the very last one, and then I applied phi H to the first component. So now we've got the parametric pair structure. We have the finite sequences structure defined in such a way we can lift the Euster twice. So we do that first of all for the finite sequence. So we provided that sigma type is a Euster, then we have that the finite sequence structure is also a Euster. Okay, and we had that parametric pairs whose H type was a Euster were themselves a Euster. Therefore, as a corollary, we can lift that all the way to the finite sequence. Okay, and so what is nice about this is that you can have such a nested type of structure depending on the needs of your theory. So for this case was having these pairs where you have this extra refusal information that's being kept in the trace. And that means all the kinds of information could be kept in the trace just as well. So in summary, so in targeting these synchronous process calculi, so I've mechanized these two axioms in Isabelle UTP, defined as type classes. Importantly, I've shown also that these are 4 independent axioms, which compares with roughly 26 axioms in existing work for capturing the same sort of generalized construction. I've also established that the main results in existing work also follow from the axioms, which is again a comforting result. We have, in fact, this hierarchy of algebra. So depending on how you define your phi, you can still obtain the original monoid trace algebra. Very comforting is there was surprisingly little impact on the existing proofs that were mechanized for both of the theories of reactive designs and CSP, and at least up to that level, everything is still compatible. So this is one of the nice things about having all these mechanized, is that you can quickly check whether these things continue to hold. And so although there were some, of course, some tidying up of proofs done, structurally they were very, very similar to what we already had. So conclusions. So I've weakened the monoid trace algebra to support pre-orders. That was the main roadblock, let's say. And also the definition of R2 had to be generalized further. This means widening the foundation for reactive theories in Isabelle UTP, but in UTP more generally, not just its mechanization, of course. Future work includes integration of this infrastructure with the main Isabelle UTP distribution, exploring further weakenings of the algebra as well. So just as my colleague, when he published the original monoid trace algebra, had pointed in his paper, there were further weakenings you could explore. Here's some, but I believe this can be extended further in order to cope with other trace structures that are appearing in the literature, not only in CSP but in other synchronous process calculi as well. And so I believe that would be an avenue for quite some future work, but I expect that some things may no longer hold. So that's something for the future. Yeah, and explaining mechanization of further synchronous process calculi. So yeah, that's everything. Thank you very much.
Thank you for the interesting talk. And are there any questions or comments? The audience has the floor. I do have a question. These Unary semigroups you mentioned, they had already appeared somewhere in the literature in another form. Is that a more specialized version to your Unary semigroup trace algebras, or is that more general than the ones you have?
Yeah, you're quite right. They're already in the literature. I mean, my contribution is very specific to handling this trace structure in terms of this concatenation operator. Yeah.
And I had a question about the Isabelle UTP. Is that its own? Is that a logic in Isabelle, or is that
no?
logic?
It's not a new logic in Isabelle. No, it's basically using Isabelle Hall. So it's built on top of Isabelle Hall.
Excellent. Any other questions or comments?
So I don't know, I hear some strange background noise. Is this coming from you, Pedro, or is it Bernhard who is trying to ask a question?
I don't believe it's myself, but I can mute myself if that helps.
No, it's gone now.
Yeah. Okay.
There were some strange sounds. Yeah, sorry to interrupt.
No problem. The RoboStar group that you're in, can you tell us a bit about that? Is it some applications of these ideas? I mean, this is in order.
Yes, that's right. So So as part of RoboStar, we have a tool chain for both modeling and for verification of robotic software. So the idea is that you can have this integration of modeling and reach integration with model checkers, theorem provers. And so what you see here in the context of Isabelle UTP is very much for the verification aspect. Yeah.
Interesting. Well, thank you very much. Again, we should thank the speaker. So unmute and thank you.